Awesome. Good to go.
Okay, let me do, oh my goodness, I always get so confused on, no, that's not right. Oh, here we go, share screen. And I want to share. I always forget which is which for um, Zoom versus Google Slides. Is that showing up good? Okay, should I just go ahead? All right, I'm gonna start my, all right, so I'll be talking about traffic at the Eisenhower Tunnel in I-70 Colorado. So it's a major interstate that goes between Denver and Vail, and then also all across Colorado. So here I have a picture just of the tunnel. It kind of goes underneath a mountain. And then this is a little joke. There's an Instagram called I-70 Things, and they're always posting about how bad the traffic is and crazy things that happen. They also post funny signs like the Colorado Department of Transportation. So this is just one that got posted on their Instagram of winter is coming. So some Game of Thrones. All right. So a little background information on the area. The traffic is a constant issue on this stretch of I-70 between Denver and Vail, Colorado. There's locals that are traveling, tourists. There's three big ski resorts in the Vail area, Breckenridge, Vail, and Beaver Creek. So that's the main cause of traffic, but also it's a way to get to all the national parks in Utah. There's just a ton of people coming through. The driving conditions are also very unpredictable. There's a ton of road work in the summer, spring, and fall. And in the winter, there can be snow, there's car accidents, people rent cars without snow tires. So it can be a real mess. And Google Maps is not always accurate. I've had an experience in August where I thought I had a 10-minute drive and I was on the road for over an hour. And Google said it was completely clear. So it's not the most reliable source. You really need to check other things. And then here we just have that same website, I-70 Things. They're actually a really good source to see if anything crazy is going on, but they also post just kind of funny stuff and what to do in the fall instead of sit in traffic or make I-70 move again. So, all right. Here's the Google Maps just showing the area. So I live right over here, kind of near Beaver Creek, just for reference. And then here we have Denver. This is the stretch of highway we're going to be looking at, this I-70 route. And this is the main area we're going to focus on, the Eisenhower Tunnel. This is the tunnel you kind of have to go through in order to get to Breckenridge, Vail Village. And I just chose a map to the parking structure. Vail is kind of right here, or Beaver Creek. So you can see if you leave Denver and you have no traffic at all, it will take about an hour and a half to get to Vail. I've never gotten it that quickly, ever. So my research question were, what are the best times to travel between Denver and Vail in order to avoid traffic? So I'm looking at how does traffic vary going westbound versus eastbound on different weekdays. Also, what are seasonal variations in traffic? And I was just curious for myself if there's a statistical increase in traffic post-COVID. Knowing these high probability traffic times can help people save time. Additionally, it can show when the ideal times are to add more public transportation to and from Denver. So the data that I was working with is from the Colorado Department of Transportation. I use 6 CSV files, and they are continuous hourly traffic counts at the tunnel. So these are traffic counts from January of 2018 all the way through every day until September of 2023. And this is what my raw data looked like once I loaded those 6 CSV files into Python. So what we have here, I had to work a lot with this data before I could actually do anything with it. For instance, at this point, 2,228, the information that I needed, so I need to work with all these different variables. I needed the date, the direction, the count, the hour, the month, the weekday, the season, and how it was related to COVID. I needed to make columns of all of those. However, right now, everything except date and direction, I only have one column to work with. So this data required a lot of processing before it was I was able to get anything out of it. So we have a date. I have the date twice actually. And then we have our direction. So primary means eastbound, secondary meant westbound. So I had that. But then at this count of 2,228, I knew that that was how many cars at 4 p.m. in September on a Friday during shoulder season after COVID. So I had to get all of those into my data frame. So the first thing I did was I converted the count date column to a pandas date time, and then I changed the index to that count date. And then from that count date, I was able to pull out a weekday, a month, and a year, which was really helpful. And then I split the data frame into eastbound and westbound. And then once I had that, I was able to take that data frame and then start working with that to get what I needed from it. So this is the first data frame that I created in order to kind of get an overall trend of what was happening through the tunnel. So what we can see is I kind of ended up pulling out the hours of midnight, 6 a.m., 10 a.m., 4 p.m., and 8 p.m. And I stacked those columns on top of each other in order to create my west and east counts. So I have all of the traffic counts for those particular times. I didn't do every single time in this one just because it got overwhelming, and we can see that in the next in this visual. So this visual isn't great because it's so cluttered, but it really shows our seasonal trends and how we have the same seasonal trends going both eastbound and westbound through the tunnel. And we can see this huge dip in COVID. So we'll take a closer look at the months. So what we can see, this is the monthly mean hourly traffic through the Eisenhower Tunnel going both eastbound and westbound. And we can see the monthly variation is a result of the number of people recreating. So we can see during ski season, December, January, February, March, we have high recreation, a lot of people driving. They're driving westbound and then they're driving eastbound. Then we have less people driving in April, May, October, and November during what's called shoulder season. But then we have a lot of people back on the road again during the summer from June to September. So again, but there's not a big variation in people going westbound versus eastbound. You can also see this really well here. If we take just 1 point for each month and every year, we see this seasonal trend really, really well. So the blue lines are January and the pink are July. So we can see we have winter, then a dip into the summer, then a dip, then winter. And then we also see this big dip when COVID started in February, or in, I have the first COVID case, so in January of 2020. And then this line indicates when the resorts actually closed. However, it recovered very quickly. People were right back here. A lot of that was because it was outdoor recreation. So we still had a lot of traffic, but there was a really significant decrease in traffic right there. And you can see there's not much variation eastbound versus westbound by month. Where we do have significant differences eastbound versus westbound is when we look at hourly traffic and day of the week traffic. So we have higher volume going west on Thursday, Fridays, and Saturdays, particularly in the mornings. So we can see at 6 a.m. here, we have quite a lot of people going, quite a lot more people going westbound than eastbound. We also have a lot more people going westbound than eastbound on Thursday, Friday, and Saturday. And then we have higher volume going eastbound Sunday and Monday, particularly in the afternoon. So we have a peak in the afternoon going eastbound. And then on Sunday and Monday, you have more people going eastbound, which again is to be expected if people did a weekend trip or something like that. They drive out, they drive west on Friday or Saturday, or maybe even Thursday, and then they come back at the end of the weekend. And a really important thing to note here is there's really nothing, there's not a lot going on east of Denver. There's a big metropolis of people in Denver, and then everything where people go to do things is westbound. So it's really people live in Denver and then they recreate in the west. So now quickly, I'm going to look at the traffic changes I saw due to COVID. So this data frame I created was the average hourly traffic count for each hour of each weekday from February to April of 2018, 2020, and 2023. So I have 2018 pre-COVID, 2020 during, and 2023 post. And again, this is just a small subset of 3 months going westbound, but it does show some really interesting information. So we can see here that our median traffic, if we look at the distribution of those data points, the median is almost half of what it was pre-COVID, and it's half of what it is now post-COVID. We also see a much more regular distribution. The traffic was a lot more predictable during COVID as well. So we don't have nearly as much of a spread in traffic. That was to be expected. You can also see here, so this shows our days of the week. We have our months. February is dark blue, March is light blue, and April is this purple. And at the top, we have pre-COVID, middle is during COVID, and post-COVID at the bottom. So here what we can see is this is kind of our normal traffic in 2018. And then in 2020, we don't see a big difference in February, but when we really start to see a difference in March, and then almost no traffic at all in April during COVID, and then pretty much back to normal. There's not much of a difference at all pre and post COVID from this visual. And then if you actually look at the statistics of it, if you do a t-test between pre-COVID and post-COVID, our p-value is not significant. It's 0.39. So we can't say there's a statistical difference between those two groups. However, if you do a t-test between post-COVID and during COVID, or pre-COVID and during COVID, there's a very, very tiny p-value. So there is statistically, there is a difference between between during COVID and pre-COVID and during COVID and post-COVID. And also if we do a one-way ANOVA test, the p-value is approaching 0. It's 1.2 times 10 to the negative 20. So there's a huge statistical difference among those three groups, but there's no statistical difference pre and post-COVID. All right, now we'll get to the most important part. So these are the daily and seasonal trends in traffic through the Eisenhower Tunnel. So this data frame is showing the mean hourly traffic for each weekday during each season, going both eastbound and westbound. So here we're able to look at hours of the day, and we're able to look at the changes during the weekday. And just a reminder, the ski season is December through March, summer is June through September, and shoulder season is April, May, October, November.
Why is it called shoulder season?
It's like the shoulders of the regular season. They also call it mud season a lot because it's muddy. So that's actually why I used brown to show it here. But yeah, it's just the name for it is the shoulder season because it shoulders up against them. So so these are the daily and seasonal trends going westbound through the tunnel. And here I'm showing Friday and Saturday because those are the main days where we do have that traffic going westbound. So we have high volume in the mornings during ski seasons on both Fridays and Saturdays. So we can see these peaks in the morning where we're going to have traffic on Friday morning and on Saturday morning. I do want you to note that this axis goes up to 2,000 cars per hour on Friday, whereas this one only goes up to 1,750 cars per hour. Just to note that. And that's most likely just people going to ski. People want to get there early. They want to have the whole day. They want to make sure they get parking. So it makes sense to leave early. We also have very high volumes on Friday afternoons in both ski season and the summer. So this is likely people, if we see Friday afternoons and also to somewhat Saturday afternoons, we see people leaving Denver to go and recreate. They're going to ski, they're going to hike, they're going to do all sorts of different things. But we do have a big peak in traffic, both in the summer and in the winter, particularly on Friday afternoons. So these are those westbound trends during ski season, and this is broken down by hour and by weekday. So the one thing I want to look at first here is on Friday. So we see on Fridays, we have that little peak in the morning, but then we really have this big peak of people. And it looks like they're just getting out of work and they're heading west. So this is not a great time to be on the road. And then we also have these small peaks on Saturday morning and Sunday morning and Friday morning of people likely going to ski. And then in the summer, we actually have even more traffic than in the winter. And you really see again that peak of Friday afternoon, people leaving the city to go recreate. And then we can see during shoulder season, we just have significantly less traffic, just not nearly as many people on the road. we can see this peaks out about 1,500 cars per hour, whereas this was over 2,000 in the summer. But we still have this Friday afternoon peak. People still like to go out into the mountains to enjoy themselves on the weekend. Now we'll look at traffic going eastbound. So these trends are very different than the ones going westbound. So we have very high volumes on Saturday and Sunday afternoons. So we can see this on Saturday afternoons. We have this peak in the winter and in the summer of people going eastbound around 2, 3, 4 p.m. We also have a massive peak of people on Sunday mornings, both in the winter and in the summer. And this really, really surprised me because I was like, why are people leaving in the morning? And then I realized that the only airport in the area is Denver. So, or Salt Lake, but that's 6.5 hours from here. So the majority of tourists who are around here are going to be flying out of Denver. A lot of people are flying on Sundays to go home, and most of the flights are between 5 and 8 p.m. And I was like, oh, that makes perfect sense. But we really see this huge peak on Sunday mornings, and we'll see it really well in the next few slides. So right here during ski season, again, like I was saying, we see this big Sunday peak of morning traffic through the tunnel between about 10 a.m. and noon. And then we also have Saturday, Sunday, and Friday afternoons. We have high traffic, mainly on Saturday and Sunday, but we still do have, and that's probably during the weekdays. It's probably just genuine like rush hour, normal traffic. But normally you wouldn't expect to have rush hour traffic on Saturdays and Sundays, but those are all the people that are heading home. So this is not a great time to be on the road between about 2 and 4 p.m. Then in the summer, again, and I want to show the axes again. This one went up a little bit over 2,000, whereas up here we're well over 2,500. We're over 2,500. And again, that huge peak on Sunday mornings of people traveling eastbound. And then you really do have heavy traffic all day on Sunday. On Saturday, Sunday, and even on Friday, you still have traffic, but really heavy traffic all day on Sunday. And then shoulder season, we can see we still have that peak on Sunday morning of people traveling eastbound, but in general, much, much less traffic. There we go. All right. And here I just looked at, this is not the subset of data I was looking at. This is actually all of the data going, in this case, going westbound at 7 a.m. So what this is showing us is even though the median on Sunday is actually lower, if we take the median for the entire year, it has much more variability. So because of those peaks on Sunday morning traffic and Saturday morning traffic as well during ski season, it's making a huge spread in that data and very unpredictable traffic throughout the year. Whereas we see this as well on Sundays going eastbound at 10 a.m. The median is higher in this case because there's always people traveling on Sunday morning around 10 a.m. But you have a huge spread in how bad that traffic might actually be. So again, you just don't, it's showing that this traffic on Sunday is very unpredictable. All right. So my main conclusions, there is no statistical difference in westbound winter traffic pre and post pandemic, but there's a very clear difference in traffic during COVID. When you're driving westbound, so if you're leaving Denver to come out for the weekend, if you can't leave by 2 p.m., it's better to just wait and leave after 6 p.m. Otherwise, you might just be sitting in traffic and wasting your whole afternoon. Even during shoulder season, there is still likely to be a little bit of traffic at that time. Also, if you're going to ski on Saturday morning or Sunday morning, it's best to try to leave Denver by 5 a.m. Not only could you end up sitting in traffic if you leave later than that, you might not get a parking spot at the resort, and then it gets really complicated with what to do with your car. So it's good to try to leave that early, unfortunately. If you are driving eastbound, there's a huge spike in traffic on Sunday mornings, particularly in the summer, likely people going to the airport. So if you need to be on the road between 10 a.m. and 2 p.m., make sure to leave with plenty of extra time, or you could miss your flight. Or it's just also not a good time. If you don't have to be on the road, try not to be on the road then. But particularly if you have a flight to make, leave early. I'd say leave at least 2 hours early. I've heard of so many people missing their flights around here because of this particular tunnel. Also expect heavy traffic between 2 p.m. and 6 p.m. on Saturdays and Sundays, just to people heading home, going eastbound. So Sunday, you're pretty much could be in traffic all day. Just not great probability of no traffic. So we also have adding more public transportation to and from Denver at peak travel times could really reduce traffic. There's two companies called Bustang and Bill Mountain Express that could both expand. They both have very limited options right now for getting people to and from the mountain. And Bill Mountain Express is also really, really expensive and pretty inaccessible to most people. So those are two companies that could really expand. Bill Mountain Express could think of making a more affordable option that's not as luxurious. Also adding a toll at the Eisenhower Tunnel at peak travel times could really alleviate traffic and also generate revenue for roads. So some future work would be to analyze other continuous traffic stations in the area to see if the patterns correlate with the patterns we see at the Eisenhower Tunnel. Also analyzing traffic stations near Winter Park, Colorado. They have a commuter train there, so it'd be interesting to see if that's helped alleviate traffic. How can we decrease traffic on I-70? Unfortunately, right now, there's not good public transportation options. And there's no existing train tracks on this section of road. It's a very narrow canyon in some areas, so it's just not where they've built trains. But it'd be interesting to research how many buses would actually need to make a difference, and how can we get people to use those buses. Right now, people don't use the bus because there's barely any of them. You have to drive and park to take the bus. And then usually you end up sitting in traffic on the bus anyways. So it's kind of a big problem in the area that needs to be solved. And I have this quote from this gentleman named Christoph Stork, who's kind of a local in the area. And he says, the key is that people use public transportation if it's fast, comfortable, and has a reliable schedule. Then he continues to talk about trains, but train isn't a great option. And it made me think of the New York City subway because people use it because it's easy. It gets you where to go. You're going. You don't have to park to take the subway. The train, I mean, the 4 train comes every 2 minutes, but we don't have anything like that here. So it's just an interesting question to solve. So yeah, that's it. Thank you, everyone. Thanks for all the lessons were great. And I say thank you to Binode for all our meetings. So yeah, that's what I got.
Awesome. Any question?
Hey, Natalie, sorry, I'm gonna ask a question. Okay.
Natalie, yes.
Yeah, hi. Yeah, hi, Natalie. Great presentation, by the way. May I ask if you got a chance to look at data with regards to like collisions and various accidents that might have contributed to you know, various traffic patterns, and see if there was a pattern in those with regards to like the ski season and the other seasons where you saw clear patterns in like traffic volume on Fridays?
So I did look at on some of my box plots, I was looking at outliers, and this didn't make it into the presentation, but when you would click on some of the outliers, you could usually look up that date. And for example, if there's an outlier of 0, so if there's no one in the tunnel, I was like, oh, that means the tunnel's closed, which usually meant there was a huge accident, which often correlated to a snowstorm. So actually there were certain dates where I was Googling dates and I would see, you know, a picture of a crash, or I would look at the forecast that day and it was like a foot of snow. So there were, if you click, particularly just looking at the outliers in the box plots.
And you know what the frequency of those outliers were? Like, so if assuming that if there was at least one crash, that means that the count would be 0, right, for that given day. Do you know what the frequency of those 0 counts might be, if I'm interpreting the data correctly?
I'm not sure what the frequency was of them, but I could look.
I imagine because the Eisenhower Tunnel, that's in the mountains. Is that correct?
Yes, it's in the mountains. It's up Loveland Pass, which is
yeah. So I imagine commuter patterns would be rather unique for that kind of setting, given that there's a higher likelihood of car accidents in mountains, or at least I would assume that's the case.
Yes, there are.
Especially when there's a lot of tourism going on, and perhaps some like more, and also I don't know what the frequency of of trucks going through this tunnel is, right? Because I'm not sure, like I would assume that serves the tourism industry and maybe there's some other industries like lumber and stuff like that in the area. So yeah, I guess I'm just wondering if you ever got a chance to look at this.
I've looked at the outliers some, but I didn't do a lot with them.
Mhm.
And there also there's a lot of trucks, and you can actually look up the ratio of trucks to cars in general going through here.
Oh, interesting.
There
Okay.
are a lot of trucks as well. There
Do you
are
know do you
there
know
are
how that sorry, go ahead.
no, no, there is a road that goes around the tunnel if the tunnel is closed, but usually if the tunnel's closed, that road is closed too. So because that road is even worse at handling snow. It's like a mountain pass rather than going through the mountain. Um, so I'm sure those traffic patterns do correlate a little bit between that and that other road. Also, the tunnel closes if there's a hazmat truck going through, and then all traffic's diverted, or you just sit and wait. So there's a lot of variables in this that are hard to control for.
Of course, totally. Yeah. Well, thank you so much for answering. This was very interesting. Good
Thanks.
job.
There is a company called Via. They are like dispatcher service for public traffic. They will estimate what gonna happen in each city and optimize the like subway, optimize bus, all kind of stuff. They went IPO a few months ago.
Oh, cool. What's it
Yeah,
called?
it's
Yeah.
Via, VIA.
Okay.
Their chief data scientist was my classmate.
Oh, cool.
Yeah.
That's awesome.
He has PhD of economy, and I can send you a link. You should look into him.
Yeah, no, I will. Because that we have really unreliable as time estimations around here. Um, yeah.
I think you have some basic data you can actually do optimization algorithm on top of it. But look into VIA, and they actually publish papers around how to optimize public transportation.
Okay. Yeah, that because that's one of our biggest issues. It's also a lot of people who live here care a lot about the environment as well. So there was a huge conference called Mountain Town 2030 here, and they're trying to be, I think it's there's every town has different goals they want to meet by 2030. And they were just talking about them, but transportation is always a huge topic at these conferences because there's so many people with cars, and there's also a big move to go to electric buses. So,
Yep.
but unfortunately, we have very, very, very little transportation between Denver and the mountains right now, and it would be really interesting to see how many buses, how many people would need to take the bus to actually reduce the traffic. That'd be really interesting.
Yep. Awesome. Good job.
Thank you.
Next, let's move to Kevin. Kevin, are you here?
Yes, I am here.
Awesome. You can take from here. You can go ahead, share your screen. Thank you so much, Natalie.
Okay. Natalie, I think you need to stop sharing your screen if you could, please. Okay, cool. All right, let's move on over here. Can you see my slide deck? Cool. Let's go into a slideshow. All right, so this is my presentation for the Ames, Iowa Machine Learning Analysis Project. So jumping into it, the process I went through on this project was to start by cleaning the data, removing all null values, removing outliers, things like that. Then doing some EDA that's basically boiled down to a few basic feature transformations, and then moving into an iterative approach for model generation to see if I could get good and then better performance on my models. So to start off, data cleaning, I went through and found all of the features that had missing values. And on the right, you can see the count and percentage of the missing values for each of these. These are the top however many features. So a few of them, especially these top three, in the 90 percentages have a lot of missing values. So if we were to leave that as is, they are going to cause us some issues down the line. So how did I deal with that? First of all, I took all of the numerical columns that were missing values, and I determined whether or not I could just add 0 in. So for example, for any columns that in the pool QC, quality control, if there was simply no pool, I put 0 for pool area, or not for pool QC, but for pool area. Similarly for the garage and basement area columns, if there was no garage or basement, I just put in 0. Similarly for categorical features, if there was no basement, say, or if there was no fence for the fence feature, I put in NF or NB as a filler for no whatever that feature is. And then finally, I rounded out my data cleaning with a few imputed values. So for example, there was one particular basement row which was missing the categorical response for the basement finish. However, it did have basement area. So I knew that there was a basement attached onto this house. However, we don't know exactly what the categorical response was for that. So what I did was I just took the most commonly found variable and then just imputed that for my value. After I got finished up with my data cleaning, I decided to jump into my EDA, and that the first thing I wanted to do really was to check my linear model assumptions, because I was leaning most heavily on linear models for my predictions. So the 4 assumptions that I needed to look out for were linearity, homoscedasticity, independence of errors, and normal distribution. Before I jumped into actually making any transformations, I took a look at some charts just to see how my features were performing already. Here you can see the ground living area, which I have specifically taken out because I think it's a good representation of what you see in a lot of the area and square foot features. You can see up in the top left, when I'm checking for linearity, I can see a lot of this conic feature where the residuals are really going to start to spray out, which is going to be an issue for us with our homoscedasticity, which you can see in the top right. Reason this is an issue is as you will not have a normal distribution of your error of residuals, which you do need for a proper linear model. So similarly, in the bottom left, you can see that just the general distribution is also not normal. And then a QQ plot in the bottom right has just, again, reconfirmed what we already were able to find out from the first 3 graphs. So what did I do? First, I took the log transformation of the sale price and the ground living area, or not just the ground living area, but all of the square foot and area columns. And you can see the effect that it has on our graphs. Now they're looking a lot better. On the top left, you can see a much more linear relationship between our area features and our sale price. In the top right, we have a much more even distribution of residuals. Bottom left, we have a much more normal bell plot as opposed to the skew that we were seeing in the last slide. And then our QQ plot is looking pretty darn good, hugging that line as best, much better than we saw in the previous slide. The next thing I did was to take a look at outliers. Here's an example of a feature that has some pretty egregious outliers. The lot area compared to the sale price. You can see that there are 4, maybe 5 or 6 extreme outliers that you can see in the top left. And what that does, it's going to create a pretty ugly distribution in the bottom left. We have a massive skew to the right here, which is just going to wreck our linear models. So how did we fix that? Well, first, like I mentioned in the last slide, we did apply a log transformation, and that got us some of the way there, although you could still see some of the outliers. So then I just managed to remove those by subsetting my data based off of any lot area that is under 100,000. I think that's square feet. And the results being the scatter plot we get in the top right and the much prettier normal plot that we get in the bottom right. Similarly, I looked into our categorical features and I tried to find anything that seemed like it would really not help us in the long run. A lot of features did have some really nice, pretty box plots that were in a linear transformation or a linear relationship. And you can kind of see that here, where the more home rooms that you'll have in a home tends to creep up in sale price. However, we have these 2 rooms and 13 rooms, which really there's not much data there. And I figured keeping them would probably not be a total benefit. So I decided that there were 2 options that I had. I could either bin them in with the 3 and 12 categories or just remove them altogether. Thinking about how normal residents are, there are probably very, very few homes, not only in Ames, but across America, that have 13 rooms or 2 rooms total. So I figured I can just remove those and just focus on the 3 to 12 range. After going through that first round of EDA, I moved straight into a predictive model. And my goal for the first predictive model was to keep it as broad as possible. So I used all features in the model. So all 80, 81 features that are available in the data set. I kept them all just to see how it would perform, how a linear model would perform on the overall data set. With the goal of then, if it did not perform well, maybe trying to reduce the size of my data set to rule out things such as multicollinearity. As I mentioned, I used the log transform, removed outliers, and I also, to make the categorical data available for a linear model, I applied a dumbification process to them to make them usable. For my models, I used an 80-20 train test data split to be able to check my model to make sure that it is not overfitting. And then I used 5 different models. I used multilinear regression, ridge, and lasso, both with an alpha hyperparameter, decision tree, and random forest. So I wanted to double check just to make sure that I wasn't opening up myself to some unnecessary possible risk with multicollinearity. And where I was most worried was with the square foot and area features. I figured, if a home has X amount of square feet on their ground floor, then their basement, a lot of times, is probably going to be X size as well. So I just did a quick correlation heat map on all of the square foot and area columns. And I was actually somewhat surprised to see that there's not anything that's too over the top collinear. My cutoff that I was trying to use was 0.8. And you can see here, nothing has a correlation higher than, I think, 0.6 or 7, other than with sale price. But that's fine. That we want that. We want to be able to use the most correlated features to our sale price to find a prediction for sale price. But thankfully, nothing like our ground area or basement thing was too collinear that we had to remove it. So moving into my first pass results, as I mentioned, this is with the entire data set. I found that for ridge, my optimal alpha was 10, and for lasso, it is 0.0001. And my best performing test was ridge regression at 93% R squared, and the smallest gap I got was also with ridge regression with just a 1.5% difference in R squared. I was a little bit surprised that this model did work so well in terms of score. 93% was definitely higher than I thought we would be getting on our first pass. But I think because we were able to do those transformations to make the model work better in a linear model, or make the data work better in a linear model, and also because we were able to remove outliers and make sure that we weren't opening ourselves up to multicollinearity, our test models did perform reasonably well compared to our trained models. However, from here, I figured something that might be interesting to do would be to try to find a model that works better in terms of the gap between our train and our test data. So for my second pass, my strategy was to use my top performing features from my past one random forest model, and I used feature importance feature on sklearn, I think it is, to get this list. And as you can see, our overall qual is by far our most important feature, but then a lot of things that you might expect, such as ground living area, the size of a garage, the total basement square feet, things that are generally considered important to a home buyer, they're also in this list as well. So I chose the top 20 features from that list and again checked for collinearity, and we were all fine there. So taking that subset of only 20 features and running the same exact process with an 80-20 split, and with our 5 models, multiple linear regression, ridge, lasso, decision tree, and random forest, with ridge having alpha 1 and lasso having an alpha of 0.001. Here are the results we got. You can see I kept the past 1 data and the past 2 data to show you the difference between the two. While the past 1 data or results seem to work actually a lot better, our test R squared is much better. There is not nearly as much gap between train and test for our past 2. And in some cases, our test actually worked better than our train data, which is a little bit curious, but not going to complain about that. So I would assume if I were to be using this in the real world, I'd probably still go with our past one, just simply because our test results were still better. However, if we're really worried about making sure that our models are as accurate as they can be, and not necessarily, or our train and test be as accurate to each other as possible, then you may want to use past 2 instead. And for a third pass, I tried to come up with another strategy to see if we can get a better score. And what I tried to do was just to take the highest correlated features to the sale price, and again run that same process again with just what would be our highest correlated features. So took the top, I believe, 20 features and run the same process. And unfortunately, this model didn't do quite as well. It only had, I think the best score was an 86% for multiple linear regression and lasso. And I think that they're the same because the lasso optimal value was 0, which I believe just reverts it back to more or less the same thing as multiple linear regression. So curious that, our first pass using all of the data did perform the best, but maybe that's just because we were able to double check ourselves and make sure that we weren't open to multicollinearity or over bias there. So final findings and recommendations. As I mentioned before, the best performing model was found with ridge regression on the entire on the modified form of the entire data set. However, to get there, we did need to do a couple transformations. We needed to do some dumbifications, and we got a 93% R squared score, meaning that 93% of the variation can be explained in our model. Our most accurate train test comparison, however, came in the ridge regression of the top 20 performing features, which we again got from our random forest model from the first pass. Just some other things to think about from this data set, some feature importance. Like I mentioned earlier, when we saw on that bar graph, the overall quality of a home was far and away the most important feature in terms of affecting price. So if anyone is looking to buy a home in Ames, Iowa, and I would assume in most places around the country as well, the number one thing that you want to be looking for is just the quality of the home, the building material, and how the bones of the house are they good structurally and all that. Next would be then the size of the home, right? So the bigger the home, the more money it's going to cost. That's not too shocking, but we can see that it is supported by our data. Some things that I found to be not as important based off of the methods that I've used: neighborhood, and then features such as pools and fireplaces. However, I have some doubts. Neighborhood, I think that there might have just been too much noise. There were very many neighborhood features and probably prices all over the place. I think that if we were to take another approach on this project and focus specifically on neighborhood, we could probably find some really interesting variations there. However, that's just not what I focused on. And then additional features such as pools and fireplaces. I think that there was too much missing data. Too many homes didn't have pools or didn't have fireplaces, and it made the variables unusable or non-impactful for this process. So maybe if we were able to find a different subset of the data, or just a different data set altogether that has more of these features, so we can actually get like a good running model, we might be able to find more trend there. But like I said, for now, that was just not anything we were able to find a connection with. So there we go. Those are my findings. Are there any questions?
Cool. I know you work with Mike Sander on this project. What are the major improvement you guys worked on?
I wouldn't say like there were like major things that he told me I need to like go back and redo. It was kind of more I was finding how to do things on my own, and then maybe he was nudging me one way or the other. One thing that he tried to help me out on was the alpha values for the ridge and lasso, and then also for random forest. And I noticed that my scores were much better when I was using those hyperparameters. So that was definitely something that he helped me out with. But overall, it was mostly him just, guiding me through thought processes, how big thing that I struggled with was how to actually form my strategy. What would how do I phrase this? How do I actually go about developing the models, and like what data do I want to use? How do I want to subset the data to maybe get better results, that sort of thing. And he really helped me out with that.
That's great. Okay. I don't have any other comments. Next presentation starts at 4:30, and we're gonna look at a deep learning capstone project. And the student was in semiconductor industry, and he's using deep learning to detect the defaulting rate. So if you're interested, come back in 10 minutes. Sounds good? Thank you so much, guys. I'll see you soon.
Thanks, Vivian.
Thank you.
Hello?
Hello, Brian. I told everyone to come back at 4:30. So if you're ready, you can share screen, and we're get right on 4:30. Okay.
Okay.
Can you try if you can share the screen now?
See my screen?
Yes, it's coming up. I don't see the screen, the slide sharing. Maybe you can pull up your slide.
Yeah, could you give me a few minutes? I'm trying
Absolutely.
to do
Take
that.
your time.
Okay. Are you guys able to see the PowerPoint now?
Yes. Yes. And we will see you in 5 minutes. Okay, let's get ready. 4:30. We can get started. Brian, it's your turn.
All right. Can you guys see my screen all right?
Yes. But we cannot see your camera.
Sure. Do you guys want to see my camera?
That's fine. It's your call.
Yeah. I'll continue. So my project is about supervised grouping of electrical defects in semiconductor manufacturing. Um, and I'll go ahead with the introduction. So what is chip manufacturing? I work for a company in which we manufacture semiconductor chips. Let me see if I can move this or get rid of it. There we go. The process of manufacturing a chip is by you start with a silicon boule, and through what's typically called the CZ process, you create these wafers which are delivered to us. We process them, and then once they're processed, they're post-packaged. Um, my specific fab only does the middle part, in which we take the wafers and we process them and convert them into FETs. The previous part of the wafer vendor, like making the silicon wafers, and the post-packaging part, we don't deal with that. So my work is focused on this middle part right here. So how does the processing work? We start with a blank silicon wafer, and then through a bunch of sequential processing steps throughout the fab, we eventually build up and make the technologies that we need. I work in IGBTs, so we are working towards making these high power devices. Um, we we do have an electrical test that we do in order to verify the functionality of our devices prior to them being shipped out of the fab, and that we call that probe test. And because we are testing the actual chips that we have manufactured, then the data that we analyze here is very useful, and being able to understand that data through various, not only electrical engineering background, but using data science is extremely important for the fab and for yield. So just as a reference, one field of view of our chips can look like this, and we currently manufacture very, very big chips. So these chips are, maybe this is what, half a centimeter wide-ish. So they're pretty huge. That didn't used to be the case, but we do now. So when we measure these chips, inevitably some of them are going to fail. And the interesting part is that the chips fail in certain patterns that we've observed over time. And the patterns that some of the more common ones are here. You can see there's like a center pattern, there's a donut, there's a edge pattern here where it's just localized to the edge. That's what edge lock means. There's an edge ring, near full, etc., right? So one idea is it possible to just use, image processing methods in order to group all of the wafers which have a specific type of failure pattern, such as donut or scratch or edge ring, etc. Um, the motivation behind actually doing that is that if you can actually group all of your wafers automatically that have a specific donut structure, one, you would be able to do root cause data mining a lot easier, um, because in essence, you would have, a lot more of the bad group, saying that the bad group is the donut and the good group would be something that's completely green. Then the more failures you have, the easier it is to locate which machine or which process or which recipe is going wrong. But currently, at least in my fab, there is no way to do this automatically, and we do this manually. So either the engineer does it, or we get a tech to do it, and they help us. And then once we establish that data set, we go and we try to do some data mining to understand the deltas. So automating that would be of great help. The other thing that would help is that we could also automate the accounting. So accounting is typically a big thing in manufacturing and in all companies, of course. And at the end of the day, the engineers are sometimes asked, well, how many types of wafers failed for the donut pattern, or how many failed for the edge lock, etc. And that's very difficult to do currently. But if we were to automate that, it would be much easier to communicate with the business units and tell them, the stats of our fail rates for each type of these yield patterns. Um, some prior work. So there had initially when I thought of this project, I thought of it in a void. I was looking at what my role is in the company and what I can do to improve it. But as I dug down into the list of and into the articles that have been published, of course this isn't an original idea. People have done this in the past and are doing it currently as applied to semiconductor manufacturing. So I'm listing a few papers that I've seen where um, there's been some active results in trying to apply this to manufacturing. And the companies, there's at least these 5 companies that I see that are interested in this type of application of deep learning. These 2 papers with an asterisk, I know it's hard to see, but these two, paper number 2 and paper number 6, are important to me because at least paper number 2 was the one where they showed me they use a public data set. And using a public data set was important because my company did not give me the green light to use their data for this project. So legal said no, so I had to use a public data set. And so these 2 papers use the data set that I used for my project, um, which kind of validates that it's a good case study to use this public data set since papers have been published on it. And also overall, the concept of applying these type of clustering methods to yield patterns in manufacturing is a very active concept. It's something that is important. So the data set is called WM-811K. And it just means that there are 811,000 wafer maps. And so this data set, for me, the most important and the most recent paper that was published on it is this paper that was published in Machines. I forget, I believe it's Samsung. I forget which company published this one. But their results were very interesting. Especially this chart right here was important for me. They showed that by using sort of vanilla CNNs, um, without transfer learning or anything, some of the most difficult to recognize patterns are these scratch patterns and these localized patterns, given that the accuracy is in the high 70s to low 80s. And some of the easiest ones are these edge ring patterns, the none pattern and the center pattern, whose accuracies are above 95%. And so I, I wanted to see if I could reproduce their results first of all, but obviously using a CNN architecture um, that was kind of not original, but done from scratch, from the bottom up for this project. So diving into the data set. So as I mentioned, it has roughly 811,000 wafer maps. The raw data set comes with 5 different columns. The wafer map column is the most important one. This is where the wafers themselves are saved in each of the rows. They're encoded by zeros, ones, and twos. And this will come up in the presentation, but 0 is the padding, 1 are the good die, and 2 are the bad die, I believe. And so that's how if you were to plot these, you would see them. We have the die size, which is not really useful. The lot name, which is something specific to manufacturing, but not useful for this project. Wafer index, again, not useful. And training test label, again, not useful. And then failure type, and so really these 2 columns are the only useful ones, the failure type and the wafer map itself. The failure type is the actual labels that tells you what type of failure it is, donut, center, edge ring, etc. So those are the useful ones. Just for fun, I kind of plotted out the wafer index as a function of how many there are per index. And this gives you an idea of how many lots they use. So each lot has 25 wafers. So it seems like somebody said, all right, get me like 3,200-ish lots and download that data. But anyway, it was just me curious about how they built this data set. It's a very old data set. People have used it for at least a decade, and I couldn't find any. I didn't do much digging, but I don't know where it came from. So I don't know who put it out there. But it is public. Um, should have gotten my pointer. So some initial EDA that was done. I divided it into, well, I grouped it for the sake of didactic purposes by the train test label that came with the data set. So it came labeled with test data and training data. Really, these are useless, but I just wanted to show how many the number of maps that we have per failure type. And you can see that there are 110,000 maps that are none and 638,000 maps that are not even labeled. So the vast majority of these are either a none label or they're not labeled yet. So we're dealing with a very small amount of the 811,000 wafers that we can actually use to train us, any kind of a neural network. The other thing is the wafer map size varies quite a bit. So I added a column to calculate the wafer map size. And the largest one is 300 by 202, and the smallest one is 6 by 21. And there were 632 different sizes. So that also needs to be taken care of before we actually feed this through a CNN. Okay. So a little bit of the division of the data. As I said, the vast majority, like 79-ish% of the data has no label at all. And the label and none pattern, meaning stuff that has the none label on it, is like 18-ish%. And then only 3% of the data is stuff that has a label and has a pattern. This is the data that I used for my CNN. So I was only able to use 3%, which is roughly 24K maps, because the other has either no distinct pattern or it's not even labeled. And as I dug through this, actually, painfully, I found that within the 18% of data that has the quote unquote none pattern, there are a lot of mislabels as well, because there are a lot of nuns that look like either scratches or localized failures. So I'm not sure if I trust all of this data anyway. But looking at only this 3% slice of data, we can see all of the types. I just did a percentage of all of the actual failure types that we have. And the ones that have the smallest percent are scratch, random, and donut. Random and donut, it's not too important, but scratch is very important. And the reason that this is important is because it has a very low amount of data, and it's also one of the harder um, failure modes to detect with the CNN per the previous paper that I showed. So it's a, it's a twofer of a problem. It's hard to detect and you don't have a lot of them. So going into that, um, I did a bit of simple pre-processing. I changed a column name because it was annoying. It came in as Trian test label. It should be train test label. I changed the column data types. I added an encoding column. I had a wafer dimension column. And I had this failure number, which just encodes the failure type to a number that I can use later on. And I think that's it for the day, for the data frame. In order to resize the maps, as I said, there's like 632 different map sizes. I used a CV2 library that does, it kind of imputes the data, and you can choose how it does this. So you can do some linear imputation by area, nearest neighbors, and cubic. So what I did is I essentially tried all of them, and I just heuristically looked at the maps to understand which ones would give me the less distortion from the original map. And if you look, it's resized without anything is bad. It looks, the data doesn't resemble the original map as best as possible. Linear is also not good. Cubic is also not good. Makes these little crosses. And then it's between area near and nearest neighbor, which are the best ones. And if you look closely, nearest neighbor gets the win. So if you look at resized area, and I had to do this on a few maps, and this map that has this really funky error that kind of looks like a star is the one that kind of helped me. So if you look at area, you can see that this guy makes a cross here for some reason, but the original map has a square there, and nearest neighbor does have a square there as well. Um, it's not perfect. This square is bigger. See here it's smaller, which it should be. But overall, I thought that it was the closest one to the original. So I use nearest neighbor as my resizing algorithm. For data augmentation, I want to thank Cole because he helped me with this quite a bit when I spoke with him. I was initially doing a ton of different affine transformations. I was scaling, skewing, shearing, and doing all sorts of fun stuff. And my CNN was not working well at all. And so really the feedback that I got was you want to do rotations that that you would actually encounter when testing the actual CNN. And so one of them the only one in my mind for now at least that we would encounter would be to see a rotated version of these maps. So all I do is rotations. And essentially what I do is I have each of these maps in training rotated randomly by either, plus minus 90 or plus minus 80 degrees. So you can see these are the original maps, and then they're all randomly rotated by either plus minus 90 or plus minus 80. I think this one's minus 90 because this fat thing is here and then it goes down. So I think but anyway. So that's all I did to do the augmentation on my data. Um, I also needed to one-hot encode. It's something that we do standard for data pre-processing prior to using data for CNNs. So what I did is I I essentially took an original map, and this is where the encoding is important. So the black part of it is all the zeros. The green or the good die are ones, and the yellows are twos. And so what it does is it separates the zeros from the ones and the twos in three different maps. So if this map was, say, a 64 by 64 by 1, and it becomes a 64 by 64 by 3, kind of like, going from monochrome to RGB in an actual image. So these are the good die and these are the bad die. And here's some code of how I did it, but everybody can do it in different ways. Big shout out to Stack Exchange. They helped me optimize my code a ton because it was very terrible at the beginning, at least for the one hot encoding. Okay, so results. So I didn't put this into data prep, but I should have. I'll verbally talk to this. And I'm using custom generators in order to create both my test and my training data and my validation data. The reason I do this is because I have around 24,000 maps, and those maps are resized to a certain size, but then once they're one hot encoded, they're multiplied by 3, right? And so I have roughly 75K maps. And each time I tried to use 75K maps, my RAM would just die and Google Colab would crash. So I never had enough RAM to get beyond to even train my CNN. And so the way around that is obviously to use a generator, because a generator creates um, maps only to consume them once they're in the CNN, and then they're destroyed out of memory. And so that way you don't have to store 75K maps in memory. You can only create as many as you need for the training, and then they're not saved in memory. So creating the generators was a big help. Here's an example of my training data generator. Um, they do have to be infinite, so it just have to be an infinite loop. It's part of how Keras works. And what I do in the generator is it takes an input. The input is a data frame, which contains the maps, and a batch size, which is a batch size. I have 100 by default, but you can change that. It's the batch size for training your epochs, a map size, and let me put this somewhere else. The map size tells you what size you want to resize the maps to. I have 64 by 64 as default, but you can change that again. So as the data frame goes in, it will find your maps. The map column, it will resize the maps to whatever map size you asked it to do. It will then rotate the maps through this augmented maps thingy, and then it will one hot encode your maps through this encode images. These functions are separate functions that are within my code that I'm just referring to here. Um, and so that's essentially what the custom generator does. And then then at the end it just spits out the training and the X train and the Y train. The X train contains the maps, and the Y train contains the labels corresponding to said maps. Okay, I will continue. Oops. Okay. The CNN architecture I used was a pretty so apparently they call this a vanilla CNN. It's because it's just kind of the simplest architecture that you can use, which is what I started out with. I have my input defined here, and what I do is I put it through a 2D convolution with a 3 by 3 kernel. It then goes to batch normalization. And after it goes to batch norm, it goes through a max pooling step. It's a 2 by 2, so you half all of your images, and then you rinse and repeat. So you conv, you batch norm, you pool. You conv, you batch norm, you pool. I do this 3 times, and so that is essentially it. At the end, I flatten it out, and then I have a fully connected layer. Um, I I do 2 of them. So you can see there's one here, and there's another one over here. And then finally, in order to get the output, um, I essentially just put this through I forget right now, um, but a sigmoid, right? I always forget, sorry. And so essentially, at the output, it goes through a sigmoid function. Um, in order to classify which one of the 8 different labels the map corresponds to. So it'll give me a probability for each of the 8, and the one with the highest probability should be the one that corresponds to the predicted label. The parameters here I would kind of ignore. For optimizer, I just used what we were taught, which is to the atom optimizer. For the loss function, it was categorical cross entropy because I have more than a binary choice, and my metric was just accuracy. Um, I will speak to the parameters in a bit. So this is something that Cole helped me understand as well. I was honestly I didn't understand it, and I'm not sure if I understand it too well, but I'll do my best. So, as I changed the image size, I found that my training and my validation loss curves were completely different. So, if the image size is 128 by 128, we see a large degree of overfitting here, because obviously, my training loss is larger than my validation. At 64 by 64, I see something more that I would expect. You can see that both training and validation have similar losses up until a certain point, at which validation essentially starts to skew away from the training loss. And at this point, you can argue that overfitting has started. So it gives you a limit on the amount of epochs that you need. But for smaller ones, for smaller images, again, it kind of looks like 128 by 128. Like the difference between training and validation is quite large. And so what I understood from this, and I know Cole is on the line, so feel free to correct me if I say this wrong, but for the small images, what's happening is, I guess, a version of underfitting, because essentially, taking away pixels in order to represent the same image with a smaller density of pixels, then there's going to be more information packed into each pixel. And my kernels are going to be filtering on a coarser version of my maps. So they're only going to get very coarse, very broad features, but they're not going to get the fine-tuned details in order to make good predictions. And as I make the maps larger, you can argue, okay, so now you're making them larger, so now you should be able to get a lot of fine-tuned details. And that's true. So as you make the maps larger, the kernels, if nothing changes, they're still 3 by 3, then yes, they can learn a lot better because they're learning on larger images, which are less pixelated in a sense. But but because you do that, you also increase your total number of parameters. So you can see that from 32 by 32, I have like 42K parameters. And at 128 by 128, I have 829,000 parameters. So as you increase your number of parameters, you can overfit on the other hand. because you just have that many more weights and biases within your CNN. So I think as you make it bigger, you endanger overfitting. As you make it smaller, you endanger underfitting because you have less details that you're sending it. So there's a sweet point in between, and that's 64 by 64. Now, the recommendation is as you make it bigger, if you're overfitting, you should use a shallower a CNN or perhaps even uh, what's the word? When you remove some layers, I forget what the word for that is. But essentially, you should cut off some layers as the image size input sizes are bigger. If the image input sizes are smaller and you see some degree of underfitting, then you need a deeper network. So I could have tuned them and fixed it so that it worked for these images, but I just chose 64 by 64 for now to see how it worked because it seems ideal size for my CNN architecture. Okay. So there's two ways of obviously of evaluating your models. You can either look at the accuracy and when it deviates between train and validation or at the loss. By looking at the loss, which is what we were familiar with in the last slide, this is the 64 by 64 loss. I found that around 9 epochs is where you get a good amount of deviation. Um, uh, I just I upped it to 10 just to get a nice round number. So I use 10 epochs in training my CNN. Um, and so here are the results. After 10 epochs, my accuracy is 94-ish%, and my validation accuracy is around 90%, 89.8. So that's as good as it gets with a quote unquote vanilla CNN for this. Um, Lastly, I wanted to show, this slide is not updated. Sorry, I have an older version of this presentation apparently because I thought it was important to compare with the work in the paper, and for some reason this didn't update, sorry. Okay, that's how this slide should have been. Let's pretend you didn't see that. So even though the accuracy is around 94-ish%, that's not true for each of the fail patterns. So really near full and edge ring are the ones that have the highest accuracy. And this is interesting for me because well, no, never mind. It's very similar to what they got, right? Near full and edge ring are very high. I didn't do the none, as I said, so you can ignore this one because I found a lot of mislabeling in those. So edge ring is around above 95, and then the other one that's close to 95 is near full. So for these two, we're essentially replicating the paper's results. And then for Scratch and Donut, which are my lowest on mine, and then the localized there are the third lowest, it's similar. So Scratch is also their lowest. Donut is not. They're doing a lot better. And then for the lock, that is also the same. So these two are the lowest for them. And that they're in the bottom three for me. Um, and they're oh no, Donut is also in their bottom three. I'm sorry, I thought it was higher. Okay, so the bottom three for them is also my bottom three. But they are doing a lot better though, because my numbers for Scratch are around 72.7 or 73%. And for Scratch, they're clearly around 80. So none of their numbers are below 80%. And my Scratch predictions is around 73-ish%. So there's still more work that I can do in order to completely replicate their paper. Um, just inspecting the misclassified maps. So I always like to do this, just, look at the results heuristically and just see, with your eyeballs if you can spot anything interesting. And for me, it was, I found that a lot of the red ones here, they're either scratch localized or edge localized. So these are just saying what the paper is saying, right? These are, you know, difficult patterns to recognize. And the CNN is just confused. And so it doesn't have enough information. One way around this is that, oh, and by the way that I'm labeling this, I should have said that at the top, edge lock equal P, that means the prediction. So that means the CNN predicted that this was an edge localized, but the actual label is that it's an edge ring equal true. And so I mean, you can see how it got confused, at least for this one. Like I would have gotten confused. This looks like it's an edge localized one, but I guess the label says it's all around, so it's an edge ring. But okay. Same thing here. Like this looks like it's only on this localized version of the edge, but the label says it's an edge ring. So anyway. Um, One thing that was done in order to improve these kind of mistakes, the paper used, well, it used attention mechanisms, and it used what they call CBAM, which was kind of a filtering scheme in order to remove all of these little dots that you see here, so that the CNN can learn only what it needs to, because all of these are noise. Like if you could feed it a scratch that has only the scratch, it doesn't have all of these little dots here, then it does much better. So another way to do that is to use a denoising autoencoder. So I have that in my to-do list. Um, for some of the ones that are green here, so I have two greens. Um, I think, for example, this one, it said it was an edge lock, but it has a scratch here. So for these, either it's a composition of two or it was mislabeled in the original data set. Um, And same for here, it was random, and this says it's localized. So this doesn't look like either of them to me. It doesn't look like random. Random is the ones where they look, like all of these points that are just randomly located everywhere. This does not look like a typical random to me. So I think there's some mislabeling even within the 3% of data that I'm using that needs to be relabeled. And for the blue ones, there's two blue ones here. Those are cases where I didn't check this, but those are cases where we have two or more patterns. And I don't have it here, and my computer just died. But um, when I looked at these, the interesting thing was that the computer thought, the CNN thought it was an edge localized pattern because of this. But the actual label is a localized pattern because of this or this, I guess. But we have both of them here, and you can only give it one label. And so the edge localized is actually the one with the second highest probability, which is interesting. So I think we can use that to maybe separate these maps even further into the unique fail modes for each map. So there's some work to do when you have more than two fail modes in each map. Um, you can potentially reclassify the maps using the second highest probability prediction. So same here, it said it was a center, which you do have a center, and the true label is a localized, maybe because of this, which you could argue is a scratch as well. So again, you have two fail modes in one map, which confuses the CNN. And lastly, there's like a true failure. So this black one, it's a real failure. Like the CNN just didn't know what it was predicting. So it says it's a donut, but this no, looks nothing like a donut. It's a center. And so for this one, I would say we would need to either make deeper networks, smaller filters, maybe larger images, which would again, which would need to be optimized because you need to make a shallower network in that case. And maybe transfer learning as well. So I did it from scratch, designing it for fun, but maybe transfer learning might be the way to go in order to actually improve the algorithm at the end of the day. Um, so for future work, there was a lot of short-term work that I actually did. And I think one of the outstanding actions short-term is to use a neural network to deliver the same accuracy with less density. Um, I think what I meant to say with this is that I wanted to optimize it so that it would avoid these types of failures. So working on these, either a deeper network, larger images, but getting that accuracy up by modulating the CNN. Um, for some long-term work, it's obviously using a denoising autoencoder in order to remove those random sprinkle fails so that you could get a much cleaner image into the CNN. And maybe using attention methods, incorporating those could also help so that we could bump up the accuracy. Both of these things were things that were done in different ways in the paper. And so it would also help me reproduce the paper's accuracy results. And that's the end. Are there any questions?
I have to rely on Coast to give you some comments on the final work.
No problem. So first of all, awesome job. This is definitely definitely better than what we were looking at before, and it's also a really interesting problem. So like a couple of things, and I apologize for having said this in reverse before, which is why you were saying it this way. When you make the input image size larger, you need to make the network deeper so that it can see the same amount of stuff that a smaller image such as 64 by 64 sees. And then if you make the input image size smaller, you need to make the network shallower. Same reason. I said that in reverse before. I apologize for that.
Oh, interesting. Okay. Thank you.
Yeah, because like if you think about it, like your patch size, like the amount of pixels you're looking at is the same, but you're shoving in more. So that's the equivalent of zooming in. And that's why like I reversed that when I was typing it to you. That's what I meant by it.
Oh, I see.
Yeah, a few different things. One interesting point you brought up is the idea that there can be multiple labels. Like when you look at it visually, you could say like this could actually be scratch and edge ring or something like that. That
Yeah.
is something that obviously the data set you were using didn't have. That does not mean that you're wrong. So I kind of think that like if you were going to use this in production, say at your company or something, the idea of abilities and seeing like there's nothing saying that it has to be one, but like you can say the top one, or you can pick the top two, or you can actually like give some probabilities. That's actually useful. So I would definitely keep that.
Hmm. Okay.
I'll be curious once because like you can take this and apply this to data at your company if it's like if they say that it's okay and you're not sharing it and everything. I'll be curious just to like I don't know if you can tell me after that, but to see how it works in that case.
Yeah, I'd
I
love
think
to.
it will work
Yeah,
well.
absolutely.
Yeah. One other, well, some questions that I had when you showed your the model architecture, it didn't show any nonlinearities. Did you have any between the convolutional layers?
Oh yeah, of course. Do you mind if I open Collab? 'Cause,
Go ahead. Go ahead.
yeah, I don't know why, but my computer I was updating it right before this, which is a terrible idea to update before you present your final project.
Yeah.
Um, and uh, Yeah, so here it is. So I do ReLU as my activations and softmax as the output. Um, the
Okay,
one
yes.
thing I know is that I actually had a question is on batch norm. So it seems like a lot of people are opposed into use batch norm before or after your nonlinearity. I use it after. I don't know what your thoughts are on that.
I usually use it before, but honestly, to sidestep the whole thing, the more modern approach to this is don't use batch norm, use another kind of norm like layer norm or group norm,
Hmm.
because batch norm depends on the size of your batch, whereas the other ones don't. So there's some statistical reasons why that matters, but otherwise, eh.
Okay. Okay. It's not a big difference. Like it'll increase my accuracy by a couple of points or something, right?
Um,
Batch norm before and
it
after
just
and
like
then
so what batch norm is doing is trying to like subtract out the like it's trying to center everything. It's trying to like get everything to have mean zero standard deviation of one.
Mhm.
So if you do that prior to the nonlinearity, you still have positive and negative values. If you're doing ReLU, obviously the output is only positive. So that's part of the discussion there.
Right. Okay.
But yeah, it's sort of it's an academic debate. Whatever works better is usually the answer.
Okay. I'll take that.
Yeah. So yeah, the one thing though about like, okay, again, because your data set only has a single label, softmax is the correct thing here because you're saying like what should it be, and we're going to train it to that. Your data set has some things that are questionably labeled sometimes, probably. I mean, so does every data set. MNIST, ImageNet, they all have things that are questionable. If you get to the point in the future where you're talking about multiple possible concurrent labels, like this is scratch and edge ring, for instance,
Mm.
then I would change. I mean, you'd have to have a data set that labels it as such, but I would change your output from softmax to sigmoid so that you're talking about like independent um, values for each of those rather than it summing to one as a probability distribution.
Oh, okay. I
It's just
see.
a subtlety. Yeah.
So, hmm. So sigmoid's not normalized. It would just give me like large values that don't
Sigmoid
seem.
squashes every single output to the 0 to 1 range with the logistic function. Softmax makes sure that the entire thing sums to 1 as a probability distribution. So you can
Oh,
only have
okay.
one true output with softmax. You can have multiple true outputs with sigmoid.
I see. Yeah, and then you can just order them by highest to lowest, and maybe the top two are like the two labels that are two failure modes that you see in your wafer.
Or you say like you define some cutoff, like let's say 50%. Like if it's over 50%, like you treat the each they're logits at that point. So you're treating each one as like a 0 to 1 probability of it being true. And if it's above 50%, it's true, and you can tell how true it is. Versus softmax, which you're saying like the highest one is the most likely, and everything is a probability distribution because it sums to one.
Right. Okay. Okay. But I also got like probabilities in softmax, right? Because it gives you predictions for all eight.
Yeah, yeah, that's that you do, but there's only one true answer there. Especially that's when you're doing cross entropy, like categorical cross entropy. There's one true answer. If you're talking about like per class, the probability of it being on, and you can have multiple, then you're talking about binary cross entropy.
Oh, I see. The question is different. Okay. All right. That you're
It's
okay.
multi-class versus multi-class multi-label.
Right, right. I see. Okay, okay. That makes sense now. Thanks. Thanks, Cole.
Yep. Yeah, but awesome job.
Okay.
I saw Nazar's here. Nazar, is this something you were dealing with at Intel before?
I'm here.
Yeah,
Can you hear me well?
yeah, I can hear you well. I know you were a
Okay.
hardware engineer at Intel for 10 years. Is this some problem you dealt with before?
No, it's not because I was more of an RTL designer, which is basically just like the code before it goes to fabrication. So like just the engineering of the chip itself, and this is more related to fab issues, I guess. But I was wondering because I see a lot of um I guess like a lot of like job postings online that require like yield engineers. And I always thought, machine learning would be a great area of exploration because a lot of these processes, as Brian said, are manual. So I think this is great work. And also the way that Brian explained the semiconductor principles, I guess, relating to the dice were really well explained. I think like simple enough for all of us to understand. So great job.
Thank you.
Awesome. I think I can wrap up here. Brian, let's find a time next week to check in, and I need to do an exit meeting with you.
Okay, yeah, thank you. No, I appreciate everybody for staying late and for listening to me babble about this stuff for like plus 30 minutes. So thank you, everyone. I appreciate your time.
Sounds great.